I've decided that the best thing to do with the cross product material is to break it up into 3 small videos. In this first one, I'm just going to tell you what the cross product is in terms of how you calculate it. In the second one, we'll look at some properties of this cross product, which will be interesting and useful to us. And in the third one, I'm going to look at the logical arguments that justify some of the things that I talk about in the second video. I've found that trying to do this all at once leads to a rather rambling and disconnected discussion. Firstly, we need to talk about determinants. I'm going to imagine that I have a table of numbers that has 2 rows, AB and CD, and 2 columns, AC and BD. I'm going to define the determinant of something like that to be the following quantity. The determinant of the table ABCD, also known as the matrix ABCD, is just this number times that number minus this number multiplied by that number. So it's a simple computation. As an example, the determinant of the matrix 2, 3, 4, 5 is 2 times 5 minus 4 times 3, 10 minus 12, negative 2. As another very small example, the determinant of the matrix 3, negative 2, 4, 1 is found in the same way. 3 times 1 minus that number times that number minus 4 multiplied by negative 2. This would be 3 minus negative 8, which is 3 plus 8, which is 11. Given any matrix with 2 rows and 2 columns of numbers, calculating its determinant is perfectly straightforward. The motivation as to why you want to do that is not. Not at this time, anyway. If I have a larger matrix, the determinant of it will be defined in a recursive way. We're going to express this new thing as an expression that involves several 2 by 2 determinants, which we can then evaluate. What we're going to do is this. We're going to travel across the first row in the table, A, B, C, and as we do so, for each such number, I'm going to imagine deleting the row and column that contains the A, or the B, or the C, and writing down the smaller determinant that results. I'll take that smaller determinant and multiply it by the A, or B, or C, and then in a pattern that's very similar to the table method from integration by parts, the signs will alternate back and forth. So to begin with, I'll look at the A, and then I'm blocking from view with my markers the row and column that contains A. What's left is E, F, I, J. Continuing across the top row, I'm going to think of taking out the row and column in the table that contains the letter B. When I do that, what's left is D, F, H, J. The last number in that top row is C. If I remove the row and column that has C in it, what's left is D, E, H, I. Having formed these 3 numbers, we alternately add and subtract them. So we will write this number down, and then we will subtract the next number, and then add the other number. If we had more terms somehow, we would continue alternately adding and subtracting. Once we've got it down to this quantity is a 2 by 2 determinant, which we know how to calculate. So is that and that. So this will reduce our problem of calculating this determinant into the problem of calculating 3 easier determinants. As an example of this sort of thing, let's calculate the determinant of this 3 by 3 matrix. I'm going to go across the top row, encountering the numbers 1, 4, and 7, and for each one of those numbers, I'll think of taking out the row and column in the original matrix and then writing down a smaller determinant. Being sure not to forget, I write that one down, I subtract the next one, and then I add the next one after that, multiplying by the 1, 4, and 7, of course. And then evaluating the smaller determinants as indicated, assuming that I haven't made any arithmetic mistakes, the determinant of our 3 by 3 matrix is -6. At this time, we have no idea why this determinant is an interesting thing to look at. If you take the linear algebra class, you'll find out a lot about that. For us, we're going to use this in a rather mercenary way to define this cross product that we're interested in. Continuing my temporary mercenary philosophy here, if I give you two vectors, u and v, in terms of their components, I'm going to define u cross v to be the following thing. It's going to be the determinant of a 3 by 3 matrix, but that's where the niceness ends, because the things that are in the table are not the same kind of things. This is a vector, that's a vector, as is k. These are arrows in three-dimensional space. u1, u2, and u3, v1, v2, v3 are numbers. It's not even obvious at the onset that this is going to make any sense. What needs to happen is I need to be able to do those multiplications and adding and subtracting that we were doing previously. If we know how to do that, then this will in fact make some sense. It is very odd, though. To illustrate this, suppose that vector u has components 1, 2, and 3, while vector v has components 0, 4, and 6. Let's write down the determinant that represents this cross product and then work the details out. In this cross product business, our determinant will always have, as its first row, the three vectors I, j, and k. These are the vectors of length 1 that point out along various coordinate axes. What's written next are the components of the first vector, whatever it is. So we write in 1, 2, and 3, since those are the components of vector u. In the cross product business, the components of the last vector that you wrote down in the product will be written as the last row in our determinant here. So this will be 0, 4, and 6. If we can figure out a way to evaluate this determinant, that's what we're going to call u cross v. If I follow the same pattern that we've established previously, we now see everything will be fine. I'll write the I quantity down and then multiply by the determinant of what I get when I remove the row and column that has I in it, and the row that has I in it is the one that has all the other vectors in it too. So what results is 2, 3, 4, 6, which is a perfectly ordinary 2 by 2 determinant. Then I'm going to subtract away whatever I get, write this quantity down, j, delete the column and row that contains j, and get 1306, then add that k vector times the determinant of what you get when you remove the top row and the third vertical column. That'll be 1204. These are ordinary determinants. They shouldn't give us any problems. Since I'm trying to keep these individual cross-product videos short, I'm just going to make a couple of observations. Since we know the components of all the vectors involved, calculating this dot product is straightforward. 1 times 0 plus 2 times -6 plus 3 times 4. The first term is 0, the second -12, then add 12, and you get 0 for an answer. Look back at the dot product information. If you have two vectors, neither one of which is the 0 vector, so that they both have a well-defined direction, and the dot product of the two vectors is 0, what does that tell you about the relationship between the vectors involved? As with u, let's look at the dot product of v with this cross product thing. V has components 0, 4, and 6. U cross V is 0, -6, 4. The dot product is 0 times 0 plus 4 multiplied by -6 plus 6 multiplied by 4, which ends up being 0 plus -24 plus 24, which is 0. It could be that this is just a coincidence. It could be that this only works out for these particular u and v vectors and not any other ones. It's going to turn out that's not true, though. It's going to turn out that this is always true, and this is a fact that we're going to take advantage of in several connections. Next, we're going to explore some properties of these cross products, but we're not going to do any of the proofs. Those will be in the third video. I hope that everybody's having a good day, and I'll talk to you again soon.